Maybe we can start.
Okay.
Okay.
So I put full screen.
Yes.
Okay.
So you can keep the full screen, then I'll read out. Yeah. Yeah. So let us start.
Yeah.
Welcome everyone to webinar on PD and related areas. We are honored to have Professor Michel Chipot with us today. Professor Chipot obtained his thesis data from University of Paris 6 under Professor Chaim Bregis in 1981. Since 1995, he is working in the math department of University of Zurich. Previously, he held a position at the University of Metz, France. His research interest lies broadly in the areas of partial differential equations, numerical analysis, and nonlinear analysis. Among many others, his work on porous medium equations, configuration of crystals, asymptotic analysis on long domains has attracted immense amount of research. He has published more than 200 research articles in several prestigious mathematical journals like Journal de Mathématiques Pure Appliquée, JMPA, Archive Rational Make Analysis, ARMA, among many others. He has authored 7 books. He is on the editorial board for several important mathematical journals. His research interest has the remarkable quality of being accessible to the very beginners, yet maintaining their advanced standard throughout. And today he will be speaking on propagation of interacting species in a spatial environment. I hope you will enjoy his talk thoroughly. Professor Shipo, it's over to you now.
Okay. Thank you very much for the presentation. I'm happy to speak in India without being there somehow. My last visit in India was in September '96. I visited Bangalore, so it's a long time ago. So thank you very much, Prosenji, for inviting me to give a talk here. And since we have a problem in biology to solve these days, I decided to speak about a biological problem, and this is propagation of species in a special environment in a field near a road. I will explain that in a moment. It's a joint work with Mingming Zhang, who is a student at USTC, so this is a University of Science and Technology in China, and at the moment also in the University of Aix-Marseille in France. So let me set up the problem. So you have a domain omega L, which is a rectangle here with between minus L, and capital L is the height. So this domain is a field, okay? And the x-axis is a road. So you have two species interacting between the field and the road. So it has been observed that the roads are playing a role not only for carrying or transporting the people, but also, the mosquitoes are interested in the people traveling on the road. Introduced some 6 years ago by Berestiki, Rolkjov, and Rossi. So I will give the reference at the end of my talk. So what are the equation in this domain? So I introduce the set of V. This is a function in H1 of the field, which V equal to 0 on the boundary gamma 1. So gamma 1, this is the limit of the field, which is not on the road. All right. So the equation on the field is kind of a KPP equation, so a reaction diffusion equation, minus the Laplacian of V equal to Fv in omega L. And on the road, you have an elliptic equation minus d prime mu double prime plus mu u equal to gu plus equal to 0 at the end of the interval. And in between, so you have a connection here between the spaces in the field and the one on the road. So that is to say, dv over dn, this is the derivative, the normal derivative to the field, equal to mu u minus nu v. And this boundary condition is taking place in gamma naught. So to resume, if you want, so you have here a reaction diffusion equation, here another one, and in between you have a coupling, all right, with the derivative of the species being a linear combination of the of the two species in interacting. So here all the things are constant. D prime, mu. These are positive constant, and I will use for my talk some other constant that I call m that will appear later. So first of all, let me give you the weak formulation of this problem. So you take a function phi in V, you multiply and integrate by parts using this boundary condition here, and you get the following system of equation. You have to find a couple u and v in h10 of gamma naught for u. U is the density of population on the road and v in the field. Okay, such that, so when you integrate by parts, you get this equation where you have integrated the normal derivative, which is mu u minus nu v. Okay, when you put this guy here, then you have and take a test function in v, then the boundary condition is integrating in that. And on the road, you have this reaction diffusion equation also, where V is the solution of here. So you know you have to find a couple UV, and the principle is the following. You are going to find for some you're going to make a fixed point. So for some U on L2 of gamma naught, you're going to solve in V here, put the V here, and try to have a fixed point. So this is the idea of finding a solution to this problem. So what are the function f and g? That's our Lipschitz continuous function. So I wrote what it means here. This is I call LF and LG the Lipschitz constants of this function. In fact, you will see a little bit later that what you need really is a local Lipschitz continuity. Now, what is important is, because we are going to use some monotonicity property, is to notice that when lambda is bigger than LF, for instance, then this function is non-decreasing. Okay, so this is an easy property to see, and it will be useful for the rest. So then I will give you an example of f later, but this is f of the logistic equation, basically. So you have a bump between 0 and 1. F0 is equal to F1 is 0. F is making a bump in between 0 and 1, and F is negative after 1. So I'm interested, of course, in a non-negative solution of this system, and so this is why my f is defined only for positive value. And the same for G. I will assume that G naught is equal to 0 and Gm for some constant m is negative. Okay, if you look at the system, with this assumption, you realize right away that 0, if you take v and u equal to 0, everything vanishes here. So u v equal to 0 is a solution of this system. But of course, what I'm interested in is finding a non-trivial solution. I will consider at the end of my talk the case of two roads and also the case of a domain, a field, which is going to infinity. Okay, this is my hobby for some years now. So first, as I said, we are going to make a fixed point and we have to take a u here, solve in v, and then put the v here and solve again in u. So first of all, I'm going to study a little bit this equation when you have a u given here and when you solve in v. So this is this. Suppose that my u, I call it w now. Suppose that you take a w between 0 and m. Then, under the assumption I gave before, there exists a minimal and a maximal solution to this problem here with value in 0 mu nu over m. Okay, mu over nu times m. All right, so how does this work? First of all, you show that any non-negative solution takes this value cannot exceed this value of mu over nu times m. Why is that? So you take as a test function in your problem here, you take phi equal to v minus k plus, where k is this number here, m times mu over nu. All right. So this is a simple computation. You compute the Dirichlet norm of this function. You write it down like that. Since you have a constant here, you can forget about this constant. And then you use your equation, all right, satisfied by v. And this is what you get exactly. Now, for v bigger than k, because I remind you, I assume that this guy here, I take m such that this guy is bigger than 1. So then when you are over k, the v is bigger than k, which is bigger than 1, so the f is negative. So this is negative. So you can forget it, and you bound this by z. But, okay, we are on v bigger than k, so that is to say v bigger than this, so that is to say v nu bigger than mu m. Okay, v nu bigger than mu m. mw is smaller than m, so this is negative. All right, so it shows that any solution to my problem here will stay, any non-negative solution will stay there. So you have two other observations. First of all, that 0 is a subsolution. Indeed, if you take 0 in your equation, everything is 0 except this term here, but the w is non-negative. So you have this inequality. And k, this k here, is a super solution. Again, if you put k in your equation, so you have, okay, this is negative, this is 0, and this guy here, nu k, is bigger than nu w. All right, so you have 0 as a subsolution and k as a super solution. So you do the following. You take Z in L2 of omega L, all right? And by the Lax-Milgram theorem, you can find a Y satisfying Z. Why? Because this is a bilinear form. It's easy to show that this is coercive. Okay, you take a lambda which is positive, and so for any Z in L2 of omega L, you have a Y in V satisfying Z. So notice that if we find a fixed point for this mapping, you will have Y equal to Z, okay? So which is these two terms are going to cancel themselves out and you will get a solution of your problem, all right? The problem, the first equation that I mentioned before. So this is what I explained here. So in order to find a maximal solution and a minimal solution, you make this iteration. So you start with why not underline and why not overline, which is for one 0 and for the other one k. All right. Starting from there, you define y n underline as s of y n minus 1, and the same for the overline yn. So you have a little bit of work to do to show that this sequence is for the underline is increasing and for the overline one is decreasing. So for some function v underline and v overline, you have that the yn underline is converging towards v underline and yn overline is converging towards v bar. Now, clearly, you know from the equation here, when you pass to the limit, you get a fixed point, all right? So v underline and v overline are fixed points for S and are solution of my initial problem corresponding to W. So that is to say, I can go back to the result. If I take a W, which is between 0 and m, in L2, in fact, in L infinity of gamma naught, then I can find a minimal and a maximal solution to this problem. Okay, this is for that. Now I'm going to try to find a case where this solution, in fact, these two solutions coincide and you have uniqueness of the solution of this problem. First of all, with the minimal and the maximal solution, I'm not sure that the minimal solution is not 0. So this is what I would like to avoid. So for that, I introduce a condition here, and I introduce the first eigenvalue and the first eigenfunction of the Dirichlet problem in the field. So that is to say, lambda 1 is the smallest lambda such that the minus Laplacian of phi1 is equal to lambda 1 phi1, phi1 equal to 0 on the whole boundary of the field, okay, on the whole rectangle. And of course, you know that this function is defined up to a constant. So I fix the constants by taking the value of phi1 equal to 1 on the point 0 L over 2. Okay, so in the middle of the field and exactly in the middle of the field. All right, so and I will suppose that lambda 1 is less or equal to fs over ds. D is the diffusion of the diffusion coefficient of the equation in the field. Okay, I will give later some example where this condition holds. Then under this assumption, for epsilon positive, the maximal solution V bar is bounded away from zero and is bounded from below by epsilon phi1. All right. So it gives me a non-trivial solution of this first equation when I fix the W. All right. So you just look at the condition I have, which is here. Okay, so it means that when you take when you take S equal to lambda 1 phi 1 equal to epsilon phi 1, I'm sorry, for epsilon small enough, you have this condition. Okay, this is just my condition here taken for S equal to epsilon phi 1. So you plug this in, and for epsilon small, you have this. Okay, then I claim that when you have that, epsilon phi 1 is a sub-solution of the problem. So first of all, my phi is I take a phi which is positive and in V, and I compute the equation with epsilon phi 1. So the term, if you go back to the equation, when you compute this quantity here, this guy disappears because phi 1 is 0 on gamma naught. So this is equal to that. All right. Now you write this using the divergence formula. So you can write it like this here, and you integrate by parts. So you get the derivative here of epsilon phi 1, but epsilon phi 1 is non-negative, so the normal derivative is negative. And here you use the fact that epsilon phi 1 is an eigenvalue, so you get that here. So this is less of, because this guy is less than this. Okay, I took the epsilon like that. So this is less than this, and here the W is non-negative, so it makes it yet bigger. So you get that epsilon phi 1 is a sub-solution of your problem. So you do again the same monotonicity argument. Instead of iterating starting from 0, you start iterating starting of epsilon phi 1. And of course, so you're going to reach a fixed point. Okay, it's converging again towards the maximal, the upper sequence is converging again towards a maximal solution of your problem. But since this is monotone here, this maximal solution is above epsilon phi 1, and so it's not degenerated. This is the lemma. So up to now, when I fix a W, I can solve the problem. I can solve the problem. Let me go back. Voilà. When I fix a W, I can solve this problem with a maximal solution, all right, which is bounded from below, away from 0. So now I will put a condition on F in such a way that this maximal solution is unique, and I will use it to solve my initial problem. So the condition is the following. You assume that f of s is decreasing on 0 plus infinity. Then you have the following. If V1 and V2 are positive solution of the problem corresponding to W1 and W2, then W1 less than W2 implies that V1 is less than V2. In particular, okay, so it shows that in this case, my problem 7 that I show you several times has a unique solution. So you do that. You take a function theta, which is smooth, which is equal to 0 for the t negative and equal to 1 for t bigger than 1, and which is non-decreasing. All right. Then you consider theta epsilon, a rescaling of this function. So this is a function which is 0 for t negative and growing up very quickly to 1 on an interval of length 0 epsilon. Now, if you take two functions v1 and v2 in V, I remind you that V is a space of function in H1 vanishing on the upper boundary, all right, of the field. All right, so they are in V because this function is smooth, so you multiply a bounded function by a h1 function, so everything is okay. So you can use them in the equation satisfied by V1, which is this one. So I use V2 theta of epsilon in the equation satisfied by V1 corresponding to W1, and I use the other one in the equation corresponding to W2. I make the difference, okay? So you see, you have here the same term. It's V1, V2, theta epsilon, and here V2, V1, theta epsilon. So when you make the difference, it disappears. So you make the difference, and what you get is this equal to the term in F. Okay, so you take this minus this, so you get the term in F and the term in W1, W2. All right, this is exactly what you have here. So you manipulate a little bit this. In particular, you manipulate this term here. First of all, okay, first of all, I assume that V don't want to make any mistake here. I assume that V1 is less than W1 is less than W2. All right. So then this guy here, so you integrate only on V1 bigger than V2. All right. So then this term is negative here, and so this is what you get here. Now, if you compute what it is here, you take the grad V, and the grad theta. So I will write theta prime for this quantity here, and I get the following. I get that F, the second hand, okay, is equal to that. And when you differentiate, you are going to get, again, the term grad V2, grad V1 is cancelled by this one, okay? So what you get is only the term in theta prime grad V1 minus V2, and here the term theta prime grad V1 minus V2 times V2, and here times V1. All right, so if you put this guy, if you factorize this, so you're getting exactly that. If you introduce an extra term here, minus V2 grad V2 plus V2 grad V2, all right? So you ending up with this, but this term here is negative, and so you getting this here. All right, so now it's easy. If you introduce gamma epsilon equal to that, you getting the inequality above is exactly that. Now, from the equation satisfied by V2, you get that this is bounded by Z. So you can replace here by z if you wish. But the important point is that gamma epsilon, if you compute it, okay, so this is this guy here. So this is bounded by uh, C epsilon, which means when epsilon goes to 0, this guy goes to 0, this guy goes to 0, and you get that this goes to 0, all right? So, but if you write it using the domain where v1 is bigger than v2, you get that the integral is negative, and so this domain here is of measure 0. All right. So this is what you have at the end. So to summarize, I have my problem 7, and then for any W with the condition I have, I find a unique super solution between this interval, but it's plain a rule here. So now I want to show that my initial problem has a unique, I'm sorry, has a solution which is not trivial. By the way, for uniqueness of the initial problem, we don't know how it works. So it's going like that. As I said, I'm going to make a fixed point. So I consider K, the V in L2 between 0 and n. All right. Then with some element in K, I can find a solution of this problem here, where the V bar is the super solution, is a maximal solution corresponding to this U. Okay, so I take a U here. Then I know that the problem I call 7 has a unique positive solution associated to W equal to U. All right. Then I use it here, and I find a U in H10 of gamma naught satisfying that. And the existence of a solution like that is just Lax-Milgram. Okay, now if I can show that this mapping has a fixed point, the term in eta here are going to disappear, and I will have a solution of my second equation of my system. All right. So this is a principle. So I claim that T is continuous. So perhaps I have to speed up a little bit. So you suppose that UN is converging towards U in K, all right? Then the solution corresponding to UN, the solution of 7, I call it V n bar, and it satisfies that, all right? So when it is converging in K, you can show that, of course, if you take phi equal to V n bar, then you get that this function here is bounded. Because of what? Because this is bounded, everything is bounded here. I remind you, I take a function in this set here. Okay, in this set here. Okay. All right, and then you pass to the limit. You extract a sequence, but in this, when you pass to the limit here in UN, in here you can pass to the limit weakly. You can pass to the limit also here, and here strongly. So you get that when UN goes to U, the corresponding solution here converges towards the solution corresponding to U, which is exactly the continuity of T. All right, so this is a continuity. Now you can show that T is monotone. Well, perhaps I pass on that. All right, you can show that T is monotone, and you can show that T maps K into itself. So let me go back. I remind you what I did here. Okay, I take a U in this K. So this is a set on the road. All right. I solve for this U the equation that I call 7, which is the equation on the field. Okay, I got a V bar. This V bar, I plug it in the equation on the road. All right, and I make a fixed point. So I have everything. This mapping T goes to K into K is continuous, but then you're working in H1 0 of the road, all right? So you're working, I pass here, you're working in H1 0 of gamma naught. And so in one dimension, H1 0 is contained in C alpha with C alpha equal to 1/2. So this is relatively compact in L2 of gamma naught, and by the Schroeder fixed point argument, T has a fixed point, which leads to a non-trivial solution to your problem, to your initial problem. All right. Okay, for what kind of F you can work with? Well, for instance, Fv equal to V1 minus V. So this is not Lipschitz, but if you look carefully to what we are doing, we're using the Lipschitz character only on a finite interval. And so this is okay. Now, Fv divided by V is decreasing. This is also what I use. And I have to have the lambda 1 small enough, but the lambda 1 for the square is given by p over 2l squared plus p over l squared. And when you take little l or big L large enough, you can have this as small as you wish. And so you have a solution of this problem. Now, I have to make another comment, perhaps. I show that V is bounded away from 0 because this is bounded by this epsilon phi1. Okay, but up to now I didn't show that U is non-trivial, but you can show it also. This is a little argument that I developed here, but I have no time. So I would like to show you the extension of that. So you can consider the problem with two roads. So you have your field here again, a road here, and above this second road gamma prime naught. So you can set the system with V is now the V in H1 vanishing only on the lateral boundary, and you take the reaction diffusion equation on this road and another one on this road, and you couple them with the equation of on the field. And so this is, I wrote down here the systems that you get. So this is the equation on the field. This is the equation on the road of the bottom, and this is the equation of the road of the top. And here I have incorporated the normal boundary condition. Then you get at the transition between the upper part of the field and the lower part of the field. So you assume that everything is a positive constant, and then you can show that this problem admits a non-trivial solution. Another thing that we do is we try to pass to the limit considering infinite field and infinite roads. Okay, so here I do it for one road. So I call gamma naught this one road at the bottom, like before, minus L times 0. And I define the infinite field, which is omega infinity equal to R times 0L. So the brightness of the field is the same. I define the infinite road here and the infinite top. and I consider V infinity the V in H1 log of omega infinity bar, such that V equal to 0 on the top row. The lateral boundary condition, of course, disappear at infinity, right? And H1 log, I explain what it is exactly. This is a V which are in each H1 of omega L naught for any L naught. So then, if you assume this condition here, I remind you that this corresponds to the condition when little l is equal to infinity. Then you can have a solution to the problem in this infinite domain. So in fact, it is defined for any L naught. So the equation that you get is defined for any L naught in omega L naught. So this is the equation in the field, but this is for any L naught. And this is the equation on the road also for any L naught. And you can show that there exists a non-trivial solution to this. It's important here to notice that I choose a phi1, this eigenvalue, which is normalized in such a way that it does not vanish. So this is important for the proof. So I mentioned at the beginning of my talk the previous work of Berestiki, Rojoff, and Rossi. They studied the parabolic case, but there was nothing on the elliptic case, so this is why we decided to work on that. So the paper with Ming Zhang is accepted in DCDS Series A, and I quote here some other people who more recently worked also on this reaction diffusion system. I'm ending by some commercial for the journal where I am managing editor. So this is a journal which is progressing. We are ranked Q2 by Scopus. So I will be happy to have more paper for it. And I thank you very much.
Thank you, Professor Shiko, for the wonderful talk. Now I request all the participants to write down their questions in QA and in the question and answer box. Okay. So we have got questions from Anup Bishwas. So I'll read it out for you.
Mm-hmm.
So he says that thank you for a very clear presentation. I guess one can also consider a non-divergence form operator in the field and develop similar results. Though the variational methods might not be applicable, would you like to comment on this in this direction?
Okay, yes, you can take coefficients which are not constant. Even you can take coefficients which are nonlinear, but I don't know. So the technique is a little bit touchy already with constant coefficient. So there are some possibility in this direction, but I don't know how easy it is. So
Okay. So I have a question.
mhm,
So for the equation, I think the solution that you get is positive in the first part of the talk.
mhm.
Uh, I mean, can we have a sign changing solution or is it not known? Any comments on that?
Can we have what?
Sign changing solution, second solution, which is sign changing.
This I don't know for uniqueness of the system. I don't know, and even for the uh, for the first equation, I don't know if you don't assume that this is positive or non-negative. I don't know. I didn't we didn't study this. I cannot tell.
Okay. And for the second part of the talk,
Yes.
I think I mean, we are dealing with the case that the domain goes to infinity,
Yes.
right? So, what is the rate of convergence? I mean, something of the solution. I mean, what is the rate
Yeah,
of?
yeah, okay. So you construct the solution by passing to the limit, of course, with the solution on the domain omega L, and you show that you can pass to the limit and get something which is non-trivial.
Okay.
Mhm.
So the problem on cross section or something comes into picture. No, I don't. In the limit
Say it again, the problem?
cross section,
Yes.
does it appear in the limit?
What do you mean the problem on the cross section? I don't understand what you
I mean,
mean.
generally, when we do this L goes to infinity,
Yes.
the limiting problem depends on the cross section, right? For
Ah, yes, I understand what you mean. No, here it's here we get a solution on the whole domain. Okay, so it's a little bit it's not a problem on the cross section, all right, but we solve the problem in an infinite domain. All right,
okay,
it's a little bit different of what you have in mind with. Okay, so if you pass to L goes to plus infinity for some data which are depending only on the section, then you get a solution on the section, okay, which is also a solution of the whole infinite domain. All right. Here we just build the solution on the whole domain. All right, and not on the section.
okay, okay. Uh, Thank you, Professor Shipo, for
Mhm.
this wonderful talk. And so we meet again on next Tuesday for the talk of Professor Moshe Marcus from Technion. So till then, goodbye. And I request all the participants to leave the platform. And thanking Professor Shipo again for this wonderful talk.
Well, thank you for your invitation to talk here. Okay, take care.
Okay. Sorry, Julia, I got your question only at the end. But anyway, I asked these questions.